Well, I hope that you're all not very tired and excited to try this if you didn't do it before. But before doing that, so today I'm going to kind of finish up the index notation and tell you a little bit about gradient and divergence. That's kind of my plan and the divergence theory. So hopefully we can do what I planned to do. And next week looks like a good week to have one of those class exercises, which is kind of a gentle name for a little quiz. So the way it works is that you can ask questions from me and so on. So it's not, don't worry about it too much, but that also tells you that you may need to review the things you've been seeing so far. Start. I would think that it would be on Thursday, but don't be surprised if it comes out on Tuesday. I want to see where we are going today and when it fits in the class. When we can break some subject. That's why. That's not because I want to keep you in suspense. And sometimes I may not even tell you that we have one of those. So this time I think it's good to know. So let's get started with this. So what type of object this is on either side? Do they match on either side? What do we have on the right-hand side? What do we have on the left-hand side? Both sides are vectors. So how many free indices do you expect then? One. Just one. Perfect. So let's start from the way I have written it. You may have written it differently if you have attempted this. I have basically started by thinking that this is a vector. So I have one free index, which I denote by I. And this is a cross product. So last time we learned how to formulate cross product. So think about it as A cross product, another object which is B cross product C. So you need to use permutation index. And then the first one is the free index. Remember, the first is the free, and then you have, what did we call the other ones? Dummy indices. And then you have the first object, and then the second object, which in this case, it's an object which is itself an object. Like it's kind of, that's how I look at it. You could have started from B cross product C. So don't worry if this is how you thought about it, but that would work too. So now it kind of becomes clear what we want to do. So we also again learn how to write the cross product. Try to write it on your own without looking at me what I'm writing to see whether you can write it. You need a permutation, just like what I did before, but try to do it on your own if you can. So now you can look at it. I took the parentheses out because then afterwards, when we are in index notation, we can move things around. So the point is that the free index should be k. The rest, if you use R and S or something else, that's fine. But the first one should be k because this is the kth component. And now it becomes kind of easy, right? Just to make things a little bit clear, easier later on, I change permutation index ijq with kij. I could do that, right? It's the same permutation. I'm doing that because if you remember last time we learned about an identity which had something to do with two permutation symbols which start with the same index. So I kind of, that's where I'm going. Okay, and now it's the time to kind of look back in your notes, or if you trust me, if you at least remember that we talked about this product, and I told you that if you are patient enough, you can show that this is equal to, now the three indices are I, J, P, and Q here. So it's IP, J, Q, and then I, Q, J, P. Right. So that's how it will be. I used black for the rest. So this will be equal to this times IJ, BP, CQ. And then you just multiply, distribute basically. So then you'll have the two Kronecker or substitution operators that you have seen before, and then try not to make any mistakes. And now take, again, if you didn't get a chance to work on it at home, take a few seconds and try to see if you can reduce that such that it looks like right-hand side. If you can resist temptations not to look at what I'm doing, I pause also to help you. It would help you warm up. This is late in the afternoon, and you know, warming up always is good. So I go quietly. You work and I work. So if you look the free index I, left-hand side, and then you have the free indices I. And last time you learned that in index notation, we can look at the component, and that is as if we are referring to the vector. So basically we are done. So this is done. Any questions about this? Okay, so the next thing we want to look at here is change of basis. This is actually pretty important. So question.
Are we supposed to take it down to this point, or you kind of went back again?
No, I think this is good enough, right? At the end?
Yeah.
You mean to write? Please ask your question.
Yeah, I was thinking we should stop where you have EKIJ. That's the fourth line. Because now you kind of went back again, having A dot B, which is not an index rule.
No.
Yeah, the last line there.
The last line?
A dot C, yeah.
So you think I should have another line?
No. It's A dot C an index rule.
A dot C?
Yeah.
Oh, why I have written it like that?
Like that.
Because it's AQCQ.
Yeah, I think we should leave it in AQCQDI. To answer your question, to be an index rule.
Right, you could, but this you want to look to see that. That's why I started asking you what object do we have on either side, and we all agreed that these are vectors.
I feel like the last line is not index. Second to the last line is index.
Well, we have one free index on the left-hand side, and I want to go to one. The line before, you see it. If you see it immediately, it's fine. But I want to make that equity. I want to show that these are equal. So it's better to write it this way. These are nothing else but scalars, no matter how I write it. But it looks now more similar to the right-hand side, doesn't it? So I prefer to do it this way. If you see it immediately looking at AQ, CQ, AC, that's fine. But again, that may not be obvious if you want to show that left and right-hand sides are equal, right? To really show it, you want to go all the way to the end. But any other questions?
What about the placement of VA? Can you keep the VA in the right position?
Sorry?
The placement of VA and CA, can we keep it to the right side, the left side?
I don't understand your question.
The last line, the VA, that you keep it in the right side, right?
Yeah.
A dot C, right side.
Yeah, this is a scalar, so that's typical, right? You don't want to have a scalar on the other side. Typically, it's alpha times vector. So it would look strange to have a vector times alpha. But you could. This is a scalar. You can.
Yeah, because what I was worried about last line was like we are still writing the A in vector notation instead of index notation.
But those are scalars. Doesn't matter, right? Doesn't matter. Don't worry about it. Definitely, that's not something to worry about. I see your point.
Yeah.
This wasn't a question, write this in index notation. It was a question if this side is equal to the other side. So I think this is more convincing than leaving it there.
Yeah.
I think. So, any other questions, concerns, and worries about this derivation? No, I'm encouraged to see that you worry about these things. That's great. So, change of basis. So now we start kind of to use some of these things that you have learned. in explaining, for example, change of bases. So you'll see how it works. So I defined this for vectors, and then I kind of extended very fast to tensors. So that's kind of my plan to do, because vectors are much more tangible for us engineers, I think. So we learned about bases before, and I told you that here pretty much we always use an orthonormal basis. So let's just start with saying that we have a vector u, and now we know how to write it in index notation. And this vector is defined with, the components are defined with respect to an orthonormal basis that you see here. So it's orthonormal. Then you want to change the bases. So we consider another orthonormal basis. So I just use prime to show the elements. So this is also be another. So we learned that vectors stay the same. What changes when you go from one basis to the other are the components. So you can write u the same way that you wrote it before with respect to the first basis. You can kind of use the same notation and write it with respect to the second basis. The question that we are asking ourselves here is how the components in these two different bases, they relate to each other. Basically, how UI is related to u prime I. And you have seen this in some forms in other courses, so but we want to kind of derive some general formulations here. So how do we start? Well, we start from the definition of components. How would we get the component u sub I in an orthonormal basis? We just use inner product, right? This is what we learned before. And if I want to write u prime I in terms of UI, I can do exactly the same thing and write that the component is u inner product with e prime I. And u is the same vector, so I can substitute for u. Let me write this here. What I have written up there. So I can write u as uj ej. And this would be exactly the same as, I can move this to. So I basically have now a relationship between ui prime and uj, right? And this relationship is this inner product. Now, let's look to see what this inner product actually is. This inner product, you remember what the formula is? It's the magnitude of the first one times, I should write this better, magnitude of the second one times the cosine of the angle between them, and I show that with I prime j, like that. I think in the book it's like cosine of EI prime EJ, but this is a little bit shorter. And I call this Q IJ. Those magnitudes are equal to 1 because we decided in the beginning that these are orthonormal bases. So that's nothing else but basically these direction cosines. So I just continue to use red so that everything about Q, if I arrange these Qij's in a matrix, that's the matrix of direction cosines. So remember last time I said you can kind of take the components of a tensor and arrange it in a matrix format, and we use this notation for that. I put the brackets. So this is the matrix of direction cosines. Okay, so if I use this notation, you can see that I can write the above equation before the red notations like that. Right? And very similarly, if I started from writing UI in terms of U prime J, I could write, I don't repeat this. I can also write Uj or Ui as a function of U prime J. If I wanted to do that, I would start from, I started here from writing U prime I. If I started from Ui, I would do exactly the same thing, and I come here. And you probably see where I'm going. I shouldn't go too much to the margins because when I make PDF, things go. Maybe I just go to the right-hand side to write that. So if I do that, if I substitute now U prime J, if I substitute it here, UI would be Q Ji Q Ik UK. So I take the U prime from the top and substitute it here. The relationship between U prime and U, we already have it. We have defined the direction cosine matrix and Qij, we already have it. Now I want to, I'm doing this to derive some properties for Qij for this matrix. So I guess I have to move to the next, yes.
Shouldn't that one be U sub j equals Q
QJ or QIG.
Let me see. UI is QJI.
Because we have J3 on the right.
I think you're right. So I have Q, it is J, Yeah, you are right. You have to have, that didn't make sense. Thank you, yes. So, it's a little bit, it's not confusing. So UI, QIJ, just let me explain this. So QIJ is just coming here, and then you want to write U prime J. So here, you have to change this I by J. So that's why it became a little bit complicated. But I cannot use again the I because I've used it before, so I have to use another dummy index, and I chose K. That's what I did. Thanks, Fashion. Of course, I didn't make a mistake. I just do it to make sure that no one is sleeping. From time to time, you see these very intentional kind of chain indices coming up. So this is kind of what we have here. And now I'm debating with myself to go to the next page or not. Well, you can, last time I also told you that when you have a transpose of a matrix or a tensor, what do? We swap the indices. So when you look at this, we kind of cannot do much with it because it's Ji, Jk. So maybe let's go to the next page because I don't think I showed you the product of matrices. So let me first quickly, it's like in orange. Whenever something is in orange, it's like something in between, coming in between. If you are multiplying two matrices, what is wrong? So if I'm multiplying two matrices, then this may be familiar to you, right? In index notation, this is how it works. Does anyone need more explanation about that? This is something I think everyone has seen. So have this in mind, and let me write down this relationship between UI and UJ again. So this is not in the same format, right? What do I have to do to make this a multiplication? I need to transpose one of those Q's. Otherwise, there is not much I can do with that here. So what I'm going to do is exactly that. So I write this as, okay, so that would be QTIJ, QJK, UK, right? Making sure I'm not making any more mistakes today. And so this is one side of the story. And the other side is you see that UI is becoming magically UK. There is something we learned last time which does that. So what do you think these product of QTIJ, QJK, what does it amount to? What operator I have to use? Yes, so that we call that substitution operator. So that's what kind of brings I to K. So what should I write here? Delta what? IK, right? Or KI, it's the same thing. Okay, I'm almost there. So what we see up there is kind of, it is as if I'm multiplying the transpose of Q with itself, and I'm looking at which component IK. So, and last time we also looked at identity tensor, right? Identity matrix. So I hope that then you see immediately that the transpose of T, Q, I keep saying T, times Q is basically the identity tensor. And you can show that similarly, that basically this also holds. So what does that tell you? Tells you that this matrix or tensor, this matrix that we are talking about matrix right now, this, the inverse is equal to the transpose, right? Yes. Lynn, it's clear. It's clear. Okay. So that's one important property of this matrix. And we already learned now how to go from one base to the other. I have already taught you. So if we have this matrix of direction cosines, you have everything you need for vectors. We talked about vectors. So if I have ui prime, and if I want to go to uj, all I'm doing is bringing qij. Now I'm checking all indices to make sure I'm not making a mistake. So without showing you, because I don't think there is any need for us who are scientists and engineers who are using this, if we want to go for tensors, if you have a tensor that, now I'm using index notation, which is defined in one base, and these are all orthonormal bases. This is important. So this is how the tensor would be defined in two different bases. So T prime ij, Tij. So if you want to write T prime ij as a function of, I cannot use ij anymore, so I have used here pq. Then it turns out that it's very similar. Instead of one q, I have to have two q's. This is for second order tensor. So this is second order. And these are, so this is I and j and p and q. And something useful for us, as you will see later, is the fourth order tensor. So if we have C prime I j k l, and I want to write it in terms of C p q r s, try to guess how the form would look like, just to make sure you are awake and see. If you have any questions, I want you to write what you think you need. This is kind of a very important pencil. So some of you who are familiar with this subject, you know exactly what it is. So I was just wondering if you can write down what you see in the form. It's simple, it's more than just that what is neutral, something like that, because it's so late at night and it's so math heavy that I'm using every opportunity to ask you to do something so you are in the class. If you look at the book, and remember what these matrices are. Each one of them is a direction cosine matrix. So each one of them is, the components are looking at the cosine of the angles between different pairs of directions, right? If you look in the book, there is an example. Sorry, just give me. There is an example in the two-dimensional, or I think also three-dimensional case, so you can get a little bit more sense what's going on.
So you have a totally homogeneous
You have to wait, right? For now, this is just preliminaries, right? We get there. We get there. That's why I'm showing you this, because you're going to see. But actually, the nice thing, so isotropy is something which has to do with change of bases, right? So if the matrix doesn't change, it doesn't change form. In no matter what base you are using, you are actually writing the elasticity matrix for an isotropic material. So that's why it's kind of important. That's why this topic is important. Oh, okay, so I changed gear. Any questions about this? Whenever I give you something to work on, it's also a very good opportunity to ask me questions. So, of course, you are always welcome to ask questions, but that's a good opportunity. Now, I want to quickly go over something else that you already know, hopefully, and those are eigenvalues and eigenvectors. So, in your experience, why do they matter? Where have you used eigenvalues and eigenvectors in your professional life or personal life, if you are that kind of a person? Any other? principal spaces. Exactly. So I guess you all kind of, I hope that those few examples convinces those of you who have never used it so far that this is an important topic. Let's just define it. So now we have a tensor. And we consider a scalar and a vector. You probably know where this is going. Such that the action of the tensor on the vector is the same as scaling the vector. That's what it means. So if this holds, then lambda is an eigenvalue and the vector v is eigenvector. So sometimes people call eigenvalues particular values. And eigenvectors principal directions, and if you are familiar with this, you kind of see why this is the case. Principal directions. So let's just use that. So do you know what the word eigen means, or where does this come from? Yes, which language? It's a German word, so that's where this is coming from, and it means like particular, really. It's more like particular in German. And how do we calculate the eigenvalues and eigenvectors for a tensor? Well, it's very simple. I don't write it down, but typically the way we do it in this class is we do exactly what you did for matrices. So you take the components of the tensor, put it in a matrix format, and do whatever you did for the matrices. And I'll give you a couple of equations if you forgot how you would do it a little bit later. So one thing which is important, so I don't write those down, I trust that you know. What is important is, do you remember under what circumstances the eigenvalues are real numbers? Because I wrote real number there, but that's kind of a lie. Yes, but what does it mean then? What kind of a tensor is positive? Definitely. It's simpler than that. I don't know. You can have elements real and you get complex. I'm sorry? I heard the right answer. You talk at the same time. I don't know who said the right answer. It has to be symmetric. So it's simpler than that. So that tells me that you were sleeping because no one caught me on that. When I put lambda, a real number, someone should have said, no, not always. I'm sure you have seen cases where in calculus, where no one cares about physics, that the lambdas come out complex, right? You just download some memories, you remember that. But in this class, because we are saying all these things to actually be able to formulate physical problems, we don't really care about those cases. What we care a lot about are these real valued eigenvalues. So that's just to make sure that we all remember, write down that we need to have a symmetric matrix. So if the tensor is symmetric, and there are some other good things when the tensor is symmetric. And some of our very important tensors are symmetric, so that's the nice thing. Then all the eigenvalues are of, so I told you that you need to kind of look at the matrix form to be able to calculate them. So let me just put this kind of implicitly here. So they are going to be real valued. That's important. And you can show that if this is the case, if lambda I is the ith eigenvalue of T, we can find the corresponding eigenvector such that they form an orthonormal basis. So this is kind of important. And the way we write it is this. So they form an orthonormal basis. A question that I forgot to ask you earlier is, are the eigenvectors unique? No, you can have infinitely large number of eigenvectors, so they are not unique. But if the tensor is symmetric, which is kind of what we have, we are going to have this property that they form an orthonormal basis. And there is another thing that you can show that is kind of interesting to think about. One can show those sentences which start with "one can show" are kind of scary. Normally there are some things which are very hard to show. I don't know what your experience is, but this is typically the case. That you can write T as this summation. Why I'm not using tensor notation here? Because I have I repeated 3 times. I cannot use tensor notation, so I have to keep the summation symbol there. What does this say? What is this I have written down? They are both I. Right. What does this say? What does this, yes, Mike. Yeah, so exactly, but can you rephrase it a little bit? Exactly, so if you use that basis, then what is the form of this tensor? Why is it just I? Close, no, it's not identity. It is a diagonalized matrix tensor. Remember, somewhere in your memory, that's what you have done before. You have taken a symmetric tensor and you have done some multiplication using the eigenvectors to get a matrix which only has diagonal components. Now I'm telling you that if you use the basis, which is formed by eigenvectors, and you represent the tensor in that basis, your tensor is going to only have elements in the diagonal. That's one hard word for me to pronounce. And those values on the diagonal are the eigenvalues. That's what it is saying. Don't worry too much about it. We are not going to use it. I just like it because I wanted to emphasize that we cannot repeat the index 3 times, and just kind of for you to think about the basis. So remember, the tensor stays the same. You are just rotating the base. So there is this special base that you can use such that you have the projection of the tensor over those directions are going to be just the lambda times that direction. That's the intuition behind it. Okay. And the last thing before moving to gradient and divergence is there are some important quantities associated with a tensor, and these are the principal invariants. So let's write those down also to have it in your notes. So if we have a tensor, we have these principal invariants. Why are they called invariants? Because they don't change under change of basis, so they are the same. So invariant under the change of basis. And these are typically, you use numbers like that. The first one is the trace from last time. I hope everyone remembers what this is. The second one is a little bit more involved. And in tensor notation, And the last one is the determinant. And last time we talked about different ways to write the determinant. I just write one way. That I called row expansion. So you have the 3 rows and then I, j, k. And just kind of a reminder, if you have forgotten how to find the eigenvalues for a matrix, so kind of the matrix form of T, like in 3D, if you remember, you end up using this equation. And it turns out that this equation, you can write it in terms of the principal invariance. And you have seen this before, but for homework, you need this, so I thought to remind you of that. And if you solve this, then you get the eigenvalues, and then you have to go to the definition to get eigenvectors, and you have done this before. Questions so far? Okay. Yeah. Now it's the time to stretch, because I'm completely going to switch to something else, and that is to introduce gradient and divergence. So the idea is that we want to look at divergence theory, and I kind of have to work my way to get there. So for a while you are not going to see the index notation, but then once we finish talking about gradient and divergence and introduce the coordinate systems, we go back and we add a few other things to the index notation, and then we'll be done with the mathematics, and that would be next week. And then afterwards we can talk about mechanics, which is a little bit maybe for some of you who are engineers, it's a little bit more fun. So let's start with defining a differential. So I want to start with something very simple, but that gives us a vehicle to define gradient and divergence irrespective of the coordinate system. So this is pretty important. So I start, maybe I put a title here. Gradient divergence. That's kind of the title. But we start with defining the differential of a function, and that's kind of essential. So let's start with something very simple, like a function which is a real valued function of a real variable. It's very simple. So so let's consider a real valued function of a real variable. So I even use the things which the symbols that you probably have used in calculus years ago, talking about functions. And x D is a subset of R, and Y is also a real valued, so Y is also belongs to R. The representation of this function, as you all are familiar with, you just plot Y in terms of X, and like it's a function. And how did we define derivative for very simple real valued functions like this? Exactly. First of all, you have to ask me derivative where, right? Where do you want to calculate? So let's just take one point here, and this looks very simple to you. There is a reason I'm walking you through this. So be patient, enjoy that it's very simple, and it's late in the afternoon, and just sit back, relax, and just follow. We define the derivative with a limit. If hopefully we all remember, and this limit was that you take this x0, you go one way to define it is at least like this. You probably know the other ways too, but that's good enough for us. So if this limit existed, we call this, so if this limit exists, we call this, I would just write here, it would be equal to the derivative of this function f at that point x0. Everything is still looking great and simple. It's not difficult, it's just that it's a little bit different from what you have seen gradient and divergence before. Now, I look at the nominator. Do you all agree that I can write that as delta y, right? So I can write this change in the dependent variable, and I write it because this is important later. Change in dependent variable y. And delta x is, of course, change in the independent variable. Okay. So I guess so far everything is looking great. And then we call that, we had something called Taylor series, right? You can use Taylor series expansion, and if you do that, delta y, which is the function evaluated as at x0 plus delta x minus f x0 would be what? Delta x, right? And then the higher terms. This is double. You all know that. This is Taylor series expansion. Now, only this part, what do we call it? It is the portion, it's the portion of the change in the dependent variable y, which is linear in what? Linear in delta x, right? It's linear. We call this differential. So differential means the part of delta y which is linear in delta x. And then we use not delta y but dy for that. So this is important. So differential is the part of and notice the difference between d and delta. A part of delta y that is linear. I write this because this is important. Linear in delta x. And what else we can say about differential? It's also evaluated at a particular point, right? It's kind of, it has some ties to that point x naught. So, and evaluated at the neighborhood, like around x naught, the neighborhood of x naught. So this is kind of, that's kind of the message that I want you to see today, because this we can easily move from the scalar valued function to vector valued and so on. So dy, we all agreed that this is equal to this. Do you agree that it's a function itself, differential? It's a function of delta x, a linear function of delta x. Yeah, why not? And to have the other part being evaluated in the neighborhood of x naught included, I use this semicolon and I put x naught there, just that it is all there. I wish we had a space in this page, but we don't. To move to the next page. Now if I go back, maybe it's not a bad thing actually. If I go back, then if I want to write delta y, it would be dy. We agreed that this is a linear function in delta x, evaluated around point x naught, plus the rest, and the rest we call this higher order terms. You may have seen this in textbooks before, and these are of course higher order terms, it's also a function of delta x. And we call them higher order because these are going faster towards 0 as delta x is going towards 0. So we don't have to worry about them if we are just looking at the first order approximation. So I just write that. So pay attention, I can interchange delta x and dx, but I cannot interchange delta y and dy. X is the independent variable. It can do, if you say dx, typically you mean a smaller kind of change, x minus x naught. I can use dx or delta x, but when I say delta y, it's not the same as dy. And that's the definition of differential. Being linear, calculated around the neighborhood. Is this all clear for a real valued function of a real variable? Okay, now if this is all clear, this is going to be easy from now on. We don't care much about these functions, but we care about other kinds of functions. For example, the real valued functions of points. So let's kind of move to, we don't have much time, but we can start at least. So let's consider another function, and this one is mapping points to real numbers. So remember this Euclidean point space, so it's going from that. And what is one example of a function like that? That takes one point and maps it to a scalar value. I know what Prava wants to say. Go for it. Temperature, right? How about something which is for elasticity very important? Pressure? Pressure has direction. It's not, when you talk about a function, tell me like from where to where, but pressure it's a very simple one. If I say to you, I say, oh, that. Scalar. What's the time? Time as a function of, time is kind of a nice variable which is independent of everything, unless you consider relativity theory and stuff like that. How about density? Right? As a function of, you consider it constant a lot of times, but it doesn't have to be. Imagine a material which has different parts in it, and a composite. So it's kind of a scalar function of points, isn't it? I didn't get that kind of reaction. I was hoping for everyone says, oh yeah. So everyone says, what? Density? Okay, great. Yeah, almost done. So I can see in your faces that no, let's just stop here. Yeah, so